Good morning, everyone. We are honored to welcome Professor Emmanuel S. Pilli, Associate Professor at MNIT Jaipur and Dean of Academic Affairs at IIIT Kota, as our esteemed speaker today. With over 150 publications and deep expertise in cybersecurity, network forensics, and emerging technologies, Professor Pilli is a thought leader shaping India's security and quantum ecosystems. His work bridges academic research and practical applications, empowering the next generation of security professionals. Today, he will enlighten us on how deep learning is transforming security applications, a topic of increasing global relevance. Over to you, sir.
Yeah, shall we wait for some time or some more people join? At 11, right?
Yes, sir, 11 will start.
Yeah, sure.
Okay, please welcome Professor Emmanuel S. Pilli. I would like to introduce you, sir, again because I think it was too early. So we are honored to welcome Professor Emmanuel. He's an associate professor at MNIT Jaipur and Dean of Academic Affairs at IIIT Kota as our esteemed speaker today. With over 150 publications and deep expertise in cybersecurity, network forensics, and emerging technologies, Professor Pillai is a thought leader shaping India's security and quantum ecosystems. His work bridges academic research and practical applications, empowering the next generation of security professionals. Today, He will enlighten us on how deep learning is transforming security applications, a topic of increasing global relevance. We are truly privileged to have him with us. Over to you, sir.
Yeah. Thank you so much, Gauravji, and it's a joy for me to be here in this first conference on deep learning. First summer school on deep learning is what I tend to get. Deep learning and various applications you have discussed. So here, maybe few of my students are working on deep learning, applying to security. So the core area is security. You will find some of my papers on this aspect. Everything applied to security. So if you go into my papers, you will find the various aspects that is there. So kind of very reluctant into deep learning, I would say. I would fully, obviously, and primarily, wherever I've heard or read about deep learning, it was more on looking at aspects on computer vision or pattern recognition and related problems. And of course, these days, many applications on natural language processing. Uh, so, by and large, these were the two major aspects that are being discussed in many deep learning aspects. But slowly, in fact, my interest started with intrusion detection, where I was doing, and then I realized that most of intrusion detection mechanism is a data mining mechanism. And slowly, that is where my interest moved into various data mining algorithms and the applications thereof. So I have always applied many deep learning mechanisms, but mostly they have been coming from there. So today, what I'm trying to do is giving you a uh, broad outlook on security applications, right? And how deep learning or machine learning or a combination of them will be able to address these issues. That's my thought process. So maybe I just want to introduce some of the terms, some of the words initially, then move on to slowly trying to discuss on how they can come together. And towards the end, I will discuss one or two of my case studies, and one of my student at least who is presently working, and currently our few of our papers are under review. Those aspects maybe we'll try to showcase because I don't know how many of the content we may be able to share because they are currently under review. But yeah, we will show you a demo or we'll show you the snapshot. I'll ask my student to share some thoughts with me, right? So let's begin to depth. So I am not sure how many of you are into security or have thought about anything on network security or but these days we see a lot of papers coming in, a lot of research which is going on in aspect. But of course, journey again started with the deep learning in one sense with the GPUs that I used to handle. I used to teach a course on parallel compute where CUDA and OpenCL were taught. Right. So using GPUs, we used to run those codes and run the parallel algorithms. And slowly, maybe I somehow was shied away. You would say shy away from deep learning or the application of trying to run with some of those things. But then I was encouraged students and facilitate them to work on these implementations, and you want to do some operations and get very close, you need to understand how the underlying hardware works. So maybe I don't know how many of you are fully aware of GPUs working underneath the Colab environment, and if you really had an access to a physical GPU, the things are totally different. As Gaurav was just mentioning that we're looking at quantum. So I had the privilege last week to literally see the quantum computer in India in a Bangalore company. So they have come up with their 25 qubit quantum computer, and I was very excited to see the live quantum computer in a simple air conditioned room. But the temperature was maintained in a chamber, right, in a small chamber enclosure. where that whole quantum computer is placed. And I was seeing some of the employees accessing the quantum computer and running their codes. As of now, we are running codes on a simulator, which is actually running on a quantum machine. So we test our algorithms and things like that. So getting closer to the hardware is another challenge. Anyway, that's another topic of interest. But let me I'm hoping most of you would have heard security mode. Most of you would have read security in your BTech and MTech courses, I'm sure. But I'm not sure the cross section of people, and I'm not sure about the interest also of how many. Because just like how I don't really go into the details of other domains where I'm not working. So when I was surprised why I was invited for this, but then yeah, one reason was my paper has 800 citations, which is basically published in IEEE Communication Service into Tutorial. I will mention that details. You can download that paper and look at. So it was basically simple machine learning techniques, which have discussed how it was used to, the what do you say, the data sets which are available for network detection, network intrusions, and trying to do detection. So and then various ways of ensemble models that we can use. So that's where I think that's where my why I was chosen to be here to security, where deep learning is being used. We are very much open for that, right? So let me start my thought process to give you a brief introduction. Then basically I will take you across the cross study cross section of various things which my students are doing. So let me start share my slides. Is it visible? Yeah. Yeah. Are my slides visible? All of you are on mute, I suppose.
Yes, sir.
Gaurav, you should be able to answer.
Yes, sir. It's visible.
Moving. Right, sure. Let's. I will be discussing security and application, but of course, because first summer school on deep learning, so I will try to look at the aspects of deep learning only with security. But to give you a brief introduction, we'll start with that. So, various terms that are used in forensics. So these are three words, and all these three domains have applications of deep learning. So network security is stopping some attack to be successful. So that's something that you can try to look at, right? So that's where we can understand. So and privacy is not stopping an attack or not stopping a compromise, but it is about revealing information about something. So how you can protect the information about yourself is the challenging aspect of a post-attack scenario. It is like a post-mortem. It is and network security is like stopping the murder, and forensics is like murder has happened, and after that you are investigating who the murderer is, right? So those are things. So basically, all of them are trying to analyze data and try to give you some solutions. So that's where the security and machine learning or AI come together, where we are trying to classify, or we are trying to create clusters, or to find out who the person is based on some information. So it's basically packet information, or it's about system call information. So a variety of aspects that you can try to look at. So let's discuss some of that. So these are three major: security, privacy, and forensics is what people tend to look at, right? And then there is a triad called confidentiality, integrity, and availability. It's called the triad. So confidentiality is security must enforce. So confidentiality talks about keeping the message from unauthorized access. So only authorized people can see the message. That is the confidentiality. If unauthorized people access the users will be able to see it, so it is called confidentiality. You may not understand the message, but if you just have seen the message, or if you know that some person, so that is confidentiality. Integrity is talking about when a message is being sent from one place to other place. If somebody can see it, it becomes confidentiality. If somebody can make changes to it, right? So if you can modify that information, there is a breach of integrity. So you should there should not be any modifications. How the message was sent, the same it must be received. If no modifications are done, then you can say the message has integrity. If the some change, some between modified some part of the message, then it's said to be a breach of message, or keep the services or keep the resources available at all points of time. So whenever an authorized user wants to access the resource, it must be available physically. So that's what is called. Uh, so this is an important aspect. So confidentiality, integrity, and availability are where the attacks happen, and then you need to try to see how you can do that. And there are three more terms which are called triple A or AAA. So first one is authentication. So and the second one is authorization. So sometimes there's a question. Forensic student has asked this in PhD Viva, which is first, authentication, authorization. So a normal security person would actually answer uh, authorization is next. Authentic. Okay. Shall I? Let me just check. Okay. 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 Just give me a minute.
Sir, you are unmuted.
Sir, can you unmute another ID? Yeah, thank you. Yeah, sorry. That can actually my student was also logged in, so now I log off to that, right? Sure, let's go ahead. Sorry for the inconvenience. Sharing my screen. Yeah, yeah. Sorry for the inconvenience. Actually, we are usually using the Wi-Fi, but sometimes the net may be an issue. So I just connected to the wired connection by that time. So we were looking at. Shall I resume? We are all back.
Yes, sir. Yes, sir.
Yeah,
Sure.
sure. So we'll look at, we have discussed CIA. We'll now discuss about three aspects. So I was mentioning as a forensics researcher in my PhD. So I was asked this question of authentication and authorization, which is first. So from a perspective of a security student, we will usually answer that first you are authenticated, then you are authorized. So actually, you will log into a system, then the system resources are authorized to you to use. So that is the understanding. But my question, because I was a forensic student, so forensic researcher. So forensics is basically he looks at, okay, first before your identity is created, let us say your email ID is created or something. So first, the system administrator authorizes you to use the system. And then that is the point of time where you will first create your login ID. So I have to authorize you first. Then you will come to the system and authenticate yourself, saying that I am so and so. Please allow me to use the resources. So first I authorize you. Your email ID is created by the authorizer or the system administrator. So that was a question. So there was a big discussion, and finally my guide had to intervene and sort out the issue, but and then explain that yeah, we are coming from two different perspectives. So please understand that sometimes where we stand, our standpoint is basically depends on from where we are looking at. So we need to understand that. So authentication, authorization, and lastly, you have what is called auditing or accounting. So most of the times we have these aspects which are discussed, and most of the things are centered around this. So broadly, if you look at what I want to do, I want to work on deep learning. Many people say that, or I want to work on AI. So the question that comes to us, maybe it's that today is the last day or tomorrow is the last day. So this is a right question to ask at this time. As a critic of deep learning, I would say, can you say I am working on deep learning, or will we say I am applying deep learning to some of the domains? So synonymity is something. Deep learning is synonymous with maybe natural language processing, or maybe with computer vision or image processing as a broad umbrella. If you look at, because we are applying deep learning to solve some of the problems in various other domains. So is it a tool? Or if somebody comes to me and says, I want to do research in deep learning, I would say, do you want to design a new algorithm? Because broadly, what we have learned is various methods. You can say CNN, RNN, and so many NNs that you have, or different algorithms that you have, and then a combination of these algorithms, which you call the ensemble mechanisms, ensemble, right? So now, apart from this, is anything evolving out of these combinations? Is a new algorithm coming in? Similarly, we look at many optimization algorithms or nature-inspired algorithms which are coming in, right? And then we can apply them in combination with a lot of these algorithms, right? So when we look at a broad spectrum of these, we are not actually doing research in deep learning, but we are doing research applying deep learning to many domains. So prominent domains take the prominent interest. So many times we sometimes think if I have to deep learning, I have to work only with images. So that's something which we need to really look at. So here is a broad spectrum of what is called security, and here is many things that we are looking at. Where we are going through information security, computer security, network security, data security, application security. So these are different words that we tend to understand. So let me quickly talk about an umbrella term is what is information security. Uh, Data and information, how you differentiate. Some of you may be doing their study on data, information, knowledge, and wisdom, right? DIKW. So different levels that you have. Data is just lying that, and if you put it in perspective, it becomes information. And when you extract some pattern out of it, it becomes knowledge. And when you apply the knowledge, it becomes wisdom or a decision. So decision support systems or most of these prediction algorithms are basically wisdom coming out of the knowledge, which is trying to be extracted from information. So keeping the information secure is a big challenge. And here we see information security, and we can try to look at those aspects. So information security is a broad term, which many of the books mention, but of course you have courses on information security, courses on computer security and all. So anything per se which relates to keeping the information secure. So one of the aspects that we predominantly look at as a first step is what is cryptography. It's part of information security, and we look at it as that it is what you call what you could look at it as cryptography, encryption and decryption mechanisms, right? And trying to keep that. So by and large, we may not use deep learning mechanisms there, but that's the part of it what we are looking at, right? And various mechanisms of how these key generations are handled and how those things are handled. So let's look at it as encryption, decryption broadly. But then it also encompasses some of these words: computer security, network security, data security. So all of these are also part of information security. So when we move to the computer security aspect, it deals with a single system, which is broadly the hardware. Maybe you look at data which is stored in the hard disk, or some of the data which is like the viruses or worms which are there. Of course, you know the difference between what is a virus and what is a worm. If somebody asks you what is a virus and what is a worm, virus needs something to carry itself. So virus cannot come into your system on its own. Virus comes sitting on a document, sitting on an application, sitting inside an application, things like that. So that is what is a virus. Virus needs a medium to carry. So it needs a carrier. It can be a parasite. It has to sit on something and come into the system. So, but when it's a worm can replicate itself and send itself. It becomes it's a program which comes as an application into your system, and it can use the network resources, and it has the intelligence to send itself. So a lot of worms are worm analysis and malware analysis. A lot of work is going on deep learning approaches to doing malware analysis. So wherever the word analysis comes, obviously you know that that is where this comes. So whenever we are doing any detection mechanism, it's where this aspect comes in. And then we have network security. How is it different? Obviously, networks is a collection of hosts, becomes a network, and network of networks becomes the internetwork or the internet. And now we are seeing that the whole world is connected, and data people can view from anywhere, sitting anywhere. People can enter into some other system and access it. So that is network security. So trying to understand the data that is coming in, right? Basically, when you look at how does data come in, the term that we try to analyze is basically a packet. Networks, computer networks, if you have studied, at the network layer is the packets. The data is in the form of packets. Data initially starts off from the application. Some data may be there in the application. When the application sends the data to the transport layer, it becomes the the segments, or the words are interchangeably used, so please don't get confused. Datagrams, sometimes you call it datagrams, or the thing, and then it moves to packets. Packets becomes frames, and they are sent onto the physical layer. So these are the 5 layers that you can look at. So the application layer generates the data, and it is sent as a datagram or a segment. It comes into the network layer, becomes a packet, moves from the network layer, goes down, becomes a frame, and is sent out as zeros and ones. It moves across the data and travels forward. So that's something that you can try to look at. So that is what is network security. So if you're able to capture some data which are coming as packets into the system, analysis of packets, analysis of network logs, switches, routers, hubs. Of course, not many hubs are used these days. So layer 1, layer 2 switches, and you have the routers. So you can collect data sitting on this router or hub, router or switch, and then you can analyze them on the gateway, at the gateway level. And then you can have devices which can log out or log into that and connect there, and then get the data from there. So that's how you can look at it, right? And then of course, data security, database security is another aspect where data is stored, and you can look at that. And lastly, you look at application security, which is web applications. So when you look at web applications or apps, when you look at mobile apps, so there are different aspects that you can look at on trying to understand the application layer security or the web application security attacks. OWASP is an organization which deals with that. So this is the basic understanding. So let me move forward. Let me take you through the other aspects that we can look at. So these are the broad aspects that we can look at, these 5 aspects that we tend to look at here. Malware detection and classification is the first area that you can look at. So you can get a variety of malwares. And in fact, one of the important things that you can look at is Android is an open source. There are so many malwares being sent as part of the Android. And you may look at the Google Play Store or maybe the App Store in iPhone also. And then you will have you have a variety of tools that are there. Applications that are there. The applications are tested by Google or Apple and put on the App Store. But later, when you actually download the app and see what the app is doing or what are the communications which are happening in the app, you will see that there may be some malicious apps which are there, which sometimes we may not be able to look at or understand. What do you say? How we can how we can measure and check whether the app or whether the app has a malware inside it or not. So there are studies going on anyway, and then a lot of deep learning approaches that are applied. And broadly speaking, it's more centered around detection and classification, either intrusion detection or you are classifying the type of attacks that are coming into the data, and then you can look at that. So there is an intrusion detection system which you can look at, and broadly these are also using data mining or classification is what basically is being done. You have phishing. Phishing, you would have heard most of the websites try to do phishing, where you try to get the password by guessing or by social engineering and try to phish the data, and then you can get into a website, and it's all a simple password, and you are trying to get this password from a variety of mechanisms. Authentication and access control, password breaking is a thing, and the role-based access control is another aspect. One of the things that I would like to share today is cyber threat intelligence. Basically, we're working on dark web, where we can look at. So it is not a single system which will give you the threat perception. You cannot know what's happening because mostly dark web. We'll come into that. We'll basically introduce you what is dark web. So at that time, when you look at, you will see that there are these cyber threats which can be connected or identified or detected on a single system, but it should be multiple sources which will collaborate and then come up with information which will point out. So that's where the cyber threat intelligence comes in, and a majority of tools are coming here, what are called OS int tools. open source intelligence tools, OSINT. Some of you may be interested in security must look up OSINT tools. And apart from these 5 areas, another 5 areas that I can look at where you see deep learning being used is IoT and edge security. I will discuss one application where one of our students is recently completing his PhD. It is on IoT security, where we are working on RPL based attacks. It's a routing protocol. But then there are issues that are there, so you can look at that. Spam and fake content detection, of course, it's a kind of security attack, you would say, but natural language processing is the broad area that I would put in. But then still, we did some work. One of my student has done, and two good papers have come in. Briefly, we will discuss how they are done and how you can apply this thing. Next is digital forensics, and a new term that is coming in. Many of you may be interested. If you don't want to work in computer vision or natural language processing, you look at AI forensics, and a big area that is coming up. And of course, some of you may have already read the adversarial attacks and defense, where you are discussing GAN, right, a generative adversarial network, and you can look at that aspect. And at the same time, we also have what is called privacy preserving machine learning, PPML, where again many deep learning algorithms are used, but kind of federated learning. Maybe you would have come across federated learning, and you can look at that. So this is a combination of more domains that are there. So adversarial attacks are where you are what do you say? You are defeated into making false conclusions or wrong classifications, incorrect classifications can be done by using these things. So you train a model on dogs, and you give a dog image, and it says cat, or you give a cat image and it still says dog, or you give a dog image, if you give a cat image and it says dog, something like that, right? So this is the kind of manipulations which can done by visibly. If you look at it, it looks like a cat only, but for the machine, it looks like it's a dog, because you have manipulated the thresholds and then do that. So a lot of those attacks are coming in, and it becomes a difficult problem, because if you're using you have Digi Yatra, some of you are using, and you just go and stand, and it's basically doing a classification and searching all the images and picking up an image which is closest to you, and observing if it's 90% it's matching, because you may have shaved your head, or you may remove your mustache and something like that, but still it identifies, because it cannot say come back with the mustache, then only I will allow you. So all these things have to be handled. When you took a photograph, you had a full hair. When you had a haircut and there's very less hair showing, so it may not identify, but it puts a threshold, and then it identifies. So there's no point there, right? So it should work, and if it should work, then these adversarial attacks, which may compromise the data, has to be checked in. And of course, federated machine learning also we'll try to look at, right? So when you look at the basic thought process is intrusion detection, where you are doing anomaly-based detection and misuse detection, two approaches, right? And most of you know it. Quickly, let me take you through. So they say that a model of data flow that is monitored under normal conditions without the presence of any intrusive procedure, right? So we are trying to see if the traffic is all normal. If there is any abnormality, you will identify those abnormalities and say that it is an anomaly. So you know the natural traffic better, natural traffic or natural data which comes in the routine. If a website is there, it gets a kind of data. So all that kind of data which is normal is said to be the normal data and normal conditions, whatever the data comes. But suddenly, if there is some change data comes in, right? Most of the time, you will get an alert from your bank when you make a transaction at a very abnormal time. Let us say you're making a transaction at 12 o'clock in the night, which your whole year you have not made a transaction after 10 o'clock in the night. So suddenly you're making a transaction at 12:30 a.m., right? Middle of the night. Immediately your system, there will be a phone call coming from your bank and saying you're making a transaction. Do you want us to authorize it? So why it is coming? Because it was an anomalous, the anomaly is observed. So similarly, Maybe you collect the data on packets, you collect the data from files, or very different kinds of inputs that you look at, which come in to analyze the network security. Uh, by and large, it is network packets, or you may look at system calls, right, or network calls. So these are various things that you can look at. So this anomaly detection, what it does is it identifies it knows the normal traffic so well that it identifies the anomaly. It is something like a bank cashier, right? He immediately, when a false note comes, or a counterfeit note comes, he will immediately pull it out and say this note doesn't work. So we feel sometimes he's an expert in identifying counterfeit notes, but actually he is not good at identifying counterfeit notes. He is very good at identifying normal notes. So he's, for life, he has been doing the normal notes. So the normal notes, he knows the field, and suddenly when there is a slight difference from the field of a normal note, he'll pull it out. Whether it is a new note or an old note, he knows all the notes so well. So he knows the original well, so the counterfeit can be easily identified. That is what is called anomaly detection. Right. The second one is misuse detection. Now, when you have to do misuse detection, basically you need to identify the patterns, and you need to understand, and then you can write down that if such and such and such and such a pattern happens, it is an attack. So what you need to remember is a series of events which happen. If 1 2 3 4 5, or 3 4 2 3 1, or whatever, in those 1 2 3 4 5 numbers, if they do come in, then you say it is an attack. So what you need to do is you need to keep on remembering whether 1 you have seen, whether 2 you have seen, whether 3 you have seen, like that. So you look at a pattern that is coming in, and based on the pattern you pick up, and then you say that there is a misuse detection. So I think you understand better. So let me take you forward. So basically, actual behavior recorded in the audit trails with known suspicious behavior, it's said to be the misuse detection. So first one is anomaly, second one is misuse. So we're discussing the misuse detection now. Sorry for putting it the other way around. So misuse detection is uncovering known attacks. So there are two approaches. One is removing unknown attacks, and second one is identifying known attacks. So identifying known attacks is easy. You know a known attack, you know a pattern, you have to look for the pattern. Whenever you get the pattern, you say it is done. But when you are doing the other way around, anomaly is, you know, only the normal pattern. Any deviation from the normal pattern, you will flag it and you call it the anomaly detection. So misuse detection is fully effective in uncovering known attacks. It is useless when faced with unknown or novel forms of attacks. So if you want to simply understand, clustering will bring out novel attacks, whereas classification will bring out known attacks. Classification knows that it is either 0 class or 1 class. The class label is there. So when you have a class label, it becomes misuse detection, whether it is class label 1 or class label 2 or class label n. You know that these are all there, and one of them you try to pick in. So then it becomes what is called the misuse detection. But when you don't know what is the kind of attacks, and normal pattern, you know, regular pattern is observing, and suddenly when there is a change that is observed, it immediately picks out and says this is anomalous traffic, right? So that is becomes a cluster. So you cluster it, and then the obvious understanding is the rare classes becomes the attack, because normal traffic is more. So normal traffic modeling will be 90% is normal traffic. Only the 10% will be abnormal traffic. And there may be, you know, very rare case where somebody is actually putting the system under 90% of attack traffic and 10% of normal traffic. But still, if you model your normal traffic very well, then you can actually capture even that 90%. Two classes, you cluster the class, and then you again do some analysis on the class. So that's how you can divide the misuse detection and these things. So let's move forward. This is a simple system that you can look at, where there's a system profile, there is a data collection which is happening, and it is coming and matching the rules in the misuse detection, whether it is yes or no is the response, right? So data is collected from multiple sources, and then they are transferred. Again, data can be collected in multiple sources, multiple formats. You have to bring them into a common format. Usually these days people are using JSON. So a lot of formats, different types, they're all bringing it to the JSON format, and then analysis is done. So it becomes easy. And there are a lot of classes which are available to analyze that as well, right? So the system profile is used to characterize normal and abnormal behaviors So profile characterizes what is the normal subject behavior, and then you can find out which is not matching the normal behavior as misuse, right? So that is one thing. The second aspect, as we are looking at the anomaly detection, basically, the normal activity, and anything that is slightly deviating is an anomaly, right? That's how it becomes a anomaly detection. And the biggest limitation of misuse detection is identified by uh, anomaly detection, which is called the novel attacks, or zero-day attacks is what is the word that is called. So there is a system profile where the natural traffic, normal traffic is profiled or modeled, and then you see there is a deviation. If there is a deviation, you call it an anomaly, and then you give a response that there's an anomaly or not. And then all anomalies may or may not be true. So there are again some issues where we look at. So normal traffic is maintained and normal system profile is created. Then the anomaly detection divide, the algorithm is how close is it, how far is it, the distance. So that's where you look at clustering. A lot of distances are used, and then you can calculate that. So you report that information. But there is a problem here. Though it addresses the novel attacks, there is a problem that the false rates are high. Why is the false rate high? Because sometimes what the threshold between normal data and abnormal data or anomaly data is very thin. So sometimes this normal data, which is on this side, if you put a threshold of 80, so something like 79 or 75 is actually normal data, but it is classified as anomalous data. So that is another issue. And also, still, though they are new attacks, if the attackers model their attacks according to the anomaly detection system, if they know the thresholds correctly, and they model the stealth attacks that we call it, and they are usually hidden in the normal traffic. So they send it, they actually model the attack as a normal traffic data. So what you're looking for is a normal threshold, and these attacks are within the threshold, and then very difficult to classify them as attacks, and they can still move on. So this is broadly the detection that we can look at. So my area of interest started where I looked at classification techniques for intrusion detection. This is something what I'm talking about 2012, 2013, 10, 12 years ago. These are papers which we did, and they're at that time itself simple. I just took up 10 machine learning algorithms, took one data set, just classified, did a comparative study. So they were published and they were put on IEEE Explore, and you had 100 citations coming in, right? And another aspect later, we looked at stacking, we looked at SVM algorithm, and clubbed it with all other 10 algorithms. So maybe 10 other algorithms, SVM plus this, SVM plus that, and so on. So these were basic, simple machine learning mechanisms that we did. So this was my first interest moving from security, pure security, when I try to understand that, okay, analysis is an important aspect in security. And if somebody put it that analysis is actually 70% or 60% of the work of security. So if somebody is claiming that I'm doing security without actually doing anything on data mining or machine learning or deep learning, you can't believe it, because that how did he do that 60% analysis without using some of these machine learning mechanisms? So that's where the aspect comes in. So these were some simple survey papers, kind of just trying to categorize that and all. And this is the paper that I was talking about, where you have done an exhaustive literature review, about 45 pages of various 10 algorithms, working on two or three data sets. We have compared all the algorithms, and we had to do a comparison study. Initially, we did with the first review. The paper was rejected initially. So, because you can look at about 10 machine learning algorithms we pick up from intrusion detection. We worked on one data set and did a thorough study of how many papers have reviewed or what they achieved and their analysis results and comparison and why. So that was what was done. But slowly we moved into, they asked the reviewers, first time they rejected it, they said it's only one data. How can you generalize all these? So then we had to do it on three data sets, bring in that and do it. So a big amount of work went in. And of course, one of the important thing I noticed, I was searching for a similar paper by just removing the word machine and putting deep learning, deep there, right? Instead of a detailed investigation analysis of using deep learning techniques for either intrusion detection or computer vision. So I could not find find a paper. So maybe that's an open problem. I was discussing with Dr. Preeti Mishra, was my student and now a faculty. in Doon University. So I was discussing with her, maybe we should start a serious survey study on various deep learning techniques being applied. I'll share some of the work that we did. But of course, that's an open problem. I would say many of you can start reading. I think she reviewed about 600 papers to write this paper. So that's the kind of hard work that needs to go in. It took about 1 year from the time she started reading and the time the paper was published. So that's a big exercise and many disappointments in between. But still, once we know that 800 of my citations are coming from this one paper, it speaks of quality. And of course, some of the foreign collaborations also helped Professor Vijay Vardarajan from Australia, and we could do this. So this is something that I would like to share, right? So let me look at some approaches. So let me start with the first approach of trying to take in. Is there any questions? I would be happy before I start taking the various approaches, and I will share with you. Any questions? You can put it in a chat before I start my 2-3 case studies. I will try to present. If there are any questions, I'll be happy to answer. Otherwise, we'll start first. No questions still here. There's something we should apply deep learning to some domain if it is required and improve our understanding. Yeah, sure. The basic idea is when you claim to say I'm doing research in deep learning, you should actually try to modify an algorithm which is already existing in deep learning and try to propose a new one. And when you're looking at an ensemble model also, in fact, my supervisor discussing with me once, and with my students, we all met him once in a university. So we were having an informal discussion, and we were talking about this research on machine learning. So he said, okay, when you are able to combine multiple algorithms and see the result, why don't you combine, if you really say, I want to do a research in deep learning or machine learning, then you should actually come up with a new algorithm. You should take the 4 or 5 best aspects of various deep learning algorithms, merge them together. There may be different components. If you open up most of the codes are readily available in either of the tools that are available for us. So you can open the code and see the code either in Python or in Java, and you can look at some components which are basically there in the program, maybe 7 or 8 components. So you can study the algorithm and study the 7, 8 components which are happening, and then pick one component from one different algorithms and see how best it can go together, and then make a new combination. So that's exactly a core research in deep learning. But otherwise, let's come back to our aspects. So if there are no questions, I'm going forward. Yeah. The first approach that I was talking about would be on this aspect of how one of my students applied machine learning to various research in cloud computing. So let me take you straight away to, of course, these are publications. So here we have most of these publications where it had a survey on intrusion detection, and we had a survey on the detailed investigation I talked about. But there were 3 contributory papers. Again, one transaction paper here calling VM card, and all these 3 papers where we are looking at intrusion detection, and intrusion detection. All of them, we were looking at virtual machine introspection tool, which was helping us to get some system calls from the system, and we were analyzing. So we got a data set of system calls, and we were analyzing them. So these were the 3 major aspects. So there were other conference papers. So this is the architecture of a cloud, the hardware. We try to set up these things. So some of us, when we do security research, we want to set up the environment, live environment, and launch the attacks, collect the data, and analyze. So that was a very ambitious thing. So we tried to do it. We tried to set up a 4-node cloud, private cloud based on OpenStack on a KVM hypervisor, right? So virtual machine KVM hypervisor, how would I explain? Equivalent to your VirtualBox or VMware open source, what is it? Proprietary tool, open this thing, VMware, or open source VirtualBox is the example for hypervisor. So other names are KVM, kernel virtual machine, and the other one is Zen, XEN, right? So these are the hypervisors. So these are the hypervisors which are also called VMM, virtual machine monitors. And these virtual machine monitors create what are called virtual machines. The virtual machines are basically your own machines which are there, which you can create. You are using virtual machines, I am sure, on VMware or VirtualBox, where you can run Ubuntu on Windows, right? So these are virtual machines, and there are attacks which are happening. So this is the snapshot. But let me quickly, these are various attacks and all. So let me quickly go through the aspect of the basic thought process of where you can look at. So these are some machine learning algorithms which were used here. And you could try to get the thing. So what exactly we did was we tried to identify the system calls. So system call sequences. So now how do I identify something, how the attacks are happening, and how can I find out? So it was very difficult. So setting up a cloud was successful, but it did not run because the resources were less. Whatever we had, we did not have the full cloud resources which we wanted, so we could not set up a live cloud. But we set up an informal cloud, but we could not do that. But what we could do is we would understand how the entire components of the cloud work. So after that, we looked at hypervisor level data, and so which could also be generated or also be captured on a single machine where the hypervisor is working, and you run some applications, run some attack traffic, and collect the system calls using a tool called virtual machine introspection. Somebody in his PhD developed that virtual machine introspection tool. He got his PhD. But I would say, based on my own research and the papers that we have referred, about 500 PhDs worldwide would have been issued on that single work. So mostly somebody created a tool, and we all used the tool and generated the data, analyzed the data, and got it. So VMI, the virtual machine introspection tool, helped us to pick up the data from the tool and give us some information. So we collected these sequences, and we could get that, and then later classify these sequences and try to identify whether it is what kind of data it can come in. So we created some features, right? And so there were basically, you created benign and intrusive samples. We had monitor traffic, so we ran the attack traffic. At that time, we captured the sequences. We ran normal traffic, we captured the sequences. So that was what was being done as the first level. Then we looked at detecting maliciously modified monitored programs. So we had a lot of these programs which are there, and we could generate that, right? So we could run it on simple machines. So now the secret I would like to tell here. So did we get system calls on a cloud environment? We could not get a data set. So what I'm trying to tell you as an experience, if you want to work on security, getting a security data set may be a problem. Why everybody is looking at computer vision? There are so many data sets. Why everybody is looking at natural language problems? There are so many data sets. It's easy to create a data set. So I was attending a workshop on generative, what is that? Generative AI, right? And then people were telling that if you don't have a data set, generative AI will create a data set for you, right? One of my BTech student at that point of time, she wanted to do an internship, and we were struggling with data sets. So we got some data samples. So about 100, 150 samples we got from various sources. Then we asked her, can you generate similar samples? With a ratio of 70-30. So 30 malicious samples and 70 normal samples. But the samples must be, very varied, right? But then it must fall into these two classifications. So a very intelligent girl, she could actually go through and understand the samples, and she wrote a code to generate. So the big homegrown data set is what we can say we created, right? So what I'm trying to tell you is, when we could not get the data set, we created the data set. So that's the first point. Please note down. Getting data sets for security is a big challenge, but there are enough data sets now. So what I would say is, yeah, I think I'm not able to see the chats. Okay, what is benign? Okay, what is benign? Benign is non-malicious. Benign traffic is good traffic. Malicious traffic is bad traffic, right? So that's the word benign. So yeah, please, I'm not able to see the chat, so I'll give you time. At that time, we can check it out, right? So meanwhile, as we look at this UNM data set, so UNM data set was not a cloud data set; it was a network data set. It was network sequences of system calls. So sequence of system calls are there, and what we were getting on the hypervisor was also a system of sequence calls. So what we did is we just said we take a system call sequence data on normal network, on a, what do you say, a network system, not a cloud system, but a network. The cloud is also a network. So we took the malicious data, network data, malicious system call data from a normal data set which was there, University of New Mexico data set. So we took it, we built a classification model for that and got good results. And then we said, because the system call also will be given a similar sequence, if we apply the similar classification mechanism, we will also get the results for that. So initially, I rejected my student's proposal. Sir, I want to say like this. I said, no, this is not correct. First, set up a cloud, launch the attack, collect the data, analyze the data, and give the results. So I said, sir, that is typically not possible in next 5 years with the available resources. So what can be done? So the question that we try to look at is, then I said, why you came up with this idea? Then she showed me 3 papers which were published in 3 reputed SCI journals. So I had to accept. I said, okay, let us try, let us send. In one of these 3 journals, we'll send a similar paper. So she took up this UNM dataset details and ran the classification algorithms on that. So simple classification algorithms, and she got various results, right? And then she wrote a paper and classified 3 approaches. So there was a proposed approach, there was another paper, there was a bag of system calls, there was some ISCS paper. So these 3 papers were compared, and the proposed approach was compared, and she got better results. And based on that, a paper was published. It was published in the High Performance Computing Conference in Australia, and you could get that. The second one is where we are moving into the hypervisor layer. This was on the virtual machine layer. Now she went in and tried to create on the hypervisor layer. Now, in the hypervisor layer, we had 2 approaches, what is called VMGuard and one is VAED, 2 different papers, right? So the 2 different papers has 2 approaches, but one contribution was covered. So you had these mechanism where we tried to look at the, now you can't go into explain all these, but I'm just saying that we used the virtual machine monitor or the virtual machine introspection library, which was based as a library, which is called the libvmi. We used the libvmi library and then created this mechanism and tried to generate some, run some malicious tools. Like there was this Avast scanner, and some of these things, and they were being identified on the hypervisor, right? And we could get these on the virtual CPUs, which virtual CPU was running that thing, and what was the system call that was running on that. So this kind of information could be captured from within the hypervisor using a virtual machine introspection tool. And then we tried to create what was called the sequences. So N1 sequence, N2 sequence, N3 sequence, and all. And again, a series of system calls coming in, becoming one thing. So bag of N grams was created. So here N1, N2, N3 are N. So N grams were created. So each of them. And then you could run on multiple algorithms. We use the TF-IDF to find out the distances. And this is a mechanism which was used. And of course, this was the program which was run. Again, you see that the UNM dataset was used, and you could get that. And simple machine learning algorithms were applied on network data. And then we were showing that these kind of data are there on hypervisor, which is similar to the data on University of New Mexico. So now this is how you can try to correlate, and people are also doing like this. People are correlating, 2 different things. So I always used to say, you don't compare apple and oranges. But what you are saying is, if this is going to work with all apples, I can classify all the apples, then I can classify all the oranges. That's what we are trying to be a correlation. But then you have to prove to the reviewer who is reviewing your journal paper that you understand oranges very well, but you don't have a data set of oranges. So you took a data set of apples and classified all the apples. So hope I am clear here. And this led to the publication of the paper, and we could do these things, and we could give these system called sequences, wrote some algorithms, designed the model, two different papers. You can look at it, and then of course two different data sets. Again, you see that University of California data set was also used, evasive data set. So that is where we had the VAED, evasive data algorithms. Again, we got these extractions, and again we applied various algorithms and combined them. Fusion is the ensemble algorithm that is used, and you could get better results. We put this and made the comparison of three different techniques which are using all these, and we could come up and they were published, right? So these are variety of papers that you can look at, and the work that is going on. So I will share you some of these papers where you can do it, and then this is the MNPD comparison with variety of techniques which have come in. You see that many machine learning algorithms have been used, and you could get the results. So this is the comparison for that. So variety of works have been compared, and we could get that. So this is the first level of things. So here you see the journals that were published. So this was the VAED, concurrency and computation practice and experience. So this SCIE. Then you had the PSI Advisor, which was Journal of Intelligent Fuzzy System, which was also SCI, and the transaction paper, which was published at that time, it was on review. Now it is published in 2019 or something. It was published. VM-Guard, and then of course this was the survey paper. This is the paper I was talking about, HPCC, High Performance Computing and Communication in Australia, and it was published. This was the first paper, and then these are other small papers which are there. So with this, the entire thesis could be completed. So all the three contributions are network security contributions or cloud security contributions, I would say. And there was a big discussion between me and my student to say that please don't say network attacks on cloud is network security. If you say cloud security, you have to do hypervisor level security or the virtual machine monitor level security, not on the network level security. So you have to go into the virtualization or hypervisor or the KVM layer, and then only do it. So that is how the first aspect has come in. So I would stop here, then take you through fake detection. My student, Mr. Krishan Pal Singh, will take you through the understanding of two papers that we are trying to share. Of course, we may not be able to share the content, but we will share you the basic aspects that are there. The second aspect is about disruptive event prediction. I hope this is visible. Is it visible?
Yes, sir, it's visible.
So it is a disruptive event or a fake information that is coming. So we are trying to identify that. How do we do that is basically the idea here. So what I want to share with you is we used what are called continual machine learning and selective forgetting, some of these mechanisms of continual machine learning and machine unlearning methods, machine learning methods. So maybe you have an idea on that. But this is specifically applying to this thing. So we looked at creating a data set again. Let me bring you to create a benchmark data set. So if the network security or detection data sets or fake data sets are not available, we need to create the data set. And then we developed a disruptive event identification framework using continuous machine learning. Right, and of course unlearning and learning. So that is what we did, and then we also applied a principle called selective forgetting, because the data is going to be so huge, and because of natural language processing based data, you need to continuously do it, and as you keep on storing and adding data to a machine learning, because most of the time, machine learning fixes to a what do you say fixes to a certain range of data or one data set. But let us say I want to look at adding data every 2 weeks to the data set. So the results will keep on changing because the content keeps on changing and the focus keeps on changing. The disruptive events keep on changing. So now how do you do it? And then there is a mechanism where we use what is called selective forgetting. So where we can where it gives you a better results. Of course, these are things which are proposed. So we'll move to how the dataset is created. You can discuss. You can refer the papers. All of them are there. The author's name is Aditi Sita. She's due for her PhD submission is under review. So these aspects she has done. So she created a data set, and that was the first question that she addressed. The second question is where we would want to look at. So here is where she used the BERT API and tried to look at based on the keywords, based on, so a lot of tweets were collected over a period of time, and it is easy to collect and capture, and then based on various locations or titles or date and time, you try to capture and collect the data, right? So that is how you can get. So the two things that we are looking at is DIEVD and DISEVD, two proposals. Fortunately for us, both the papers are published in transactions, IEEE transactions. So we will look at that. So this is the DIVD paper. Sorry. Yeah, so this was Aditi Sita, Satyendra Singh, Emmanuel Pilli, where we had IEEE transaction on emerging topics in computing. 2023 it was published. Disruptive event detection. So again, as you look at it, it's basically the detection model that is being created. And as we look at, so this is how the framework works. And the three major components, as we look at the representation learning using knowledge distillation and prototype rehearsal. Then classification is the main aspect, the nearest mean of candidate events. And then finally, the candidate event selection. So this is the class incremental learning that we can try to do. So the training was done, the network loss function, and how do you do it? So that's what was the whole thing. So the data set contained about 68 830 tweets collected from 505 events during a period of time. And removing redundant and unrecoverable events. Some of them were not recoverable, so 34%. So, and the data set was collected over 1 month, and we used to understand the performance of how it goes. So these were the questions that we asked. How will it help? How is the performance? How is it going to improve? So these are again the results that we look at. So DNN, SVM, classification, algorithms which are decision tree, naive Bayes, and random forest, and we could see that the DNN could give the best results which got and in comparison with the other aspects, right? So again, there are other methods which we had looked at, and we tried to compare various mechanisms which are already there, various key mechanisms that we did, and then we tried to see whether the continuous machine learning will help in identification of disruptive in an incremental way, and we tried to look at various data sets which were there in 2012. One data set was there in the recent Twitter data set. So we looked at how the timeline was changing. So, and then we could identify different mechanisms which are applied. So you would have studied what is LSTM, by LSTM, RNN, GRU, and by GRU. So you know the I'm not going into that. So, but then this is the kind of work which goes into, right? Once you capture the data set and then you do a combination of multiple combinations. But here we see when I looked at these things, there's no new word. There is no new proposal. There's a framework proposed. There is a mechanism which is proposed, but a new algorithm is not proposed. CNN, LSTM, RNN, they are all same by LSTM, GRU by GRU. So similar things. As of now, we are doing that, but slowly we must be able to modify and get another machine learning algorithm or a deep learning algorithm. That is what. So here again, we have compared with the two multiple techniques, and then we also came up with the various versions of DIEVD, how we can try to do that. But there was no significant difference if you look at. But in some times of analysis training time, there was a significance difference. But in the trainable parameters or the incremental accuracy, there is not much of a difference. But if you try to compare that, so we also did that, and what was happening. So this is the other one was where you used selective forgetting, right? The selective forgetting, where it is went out IEEE transactions and computational social systems. This is also published. So both the papers were published, and here is where we are using selective forgetting in this. So here we have the variety of lists which are maintained, and amnesiac unlearning, right? Amnesia is where you forget, right? So machine unlearning is a process of removing or reversing the learned knowledge or patterns from a machine learning model. So you try to remove some events which have been very old and unrelated. So you try to unlearn them, right? So which helps us in improving the learning mechanism. So that's what we did. So we have variety of events which are coming in, and what has happened, and slowly as we apply these things, so they become limited in that sense. So these are the questions that we asked, and we use the ODE using the MNIST machine learning, MNIST machine learning technique, and we could see that. So various metrics, the forgetting time, the training time, incremental accuracy, and the trainable parameters, and we could do a variety of impact we could understand. And slowly we looked at various times where we have these mechanisms, unlearning, machine learning and things like that. So these are the results. And then we did an ablation study as well. Please go through the papers. I'm just giving you a snapshot. I may not be able to explain everything here. So this is the so these two papers is what I try to bring in, and you can refer these two papers. And this is basically on fake detection or fake news detection or fake event or identification or detection of disruptive events, right? So that is how we could come up with that, right? And there are the future directions which are there. So these two papers have been published, and there are other conference papers which are going on, and there one more journal she has submitted for the dataset creation is going on, and we are trying to get that. So very good contribution, and these most of the things were worked with the help of an IISc project where we got the access of the high performance computing GPU cluster from IISc, and we could remotely access and run the codes there because it was part of the project. And she was a project staff, and within no time she's now working with Volvo R&D, and we're happy. So this is something that you can look at, right? And the third case is a very recent PhD, which is still under process. He's also submitting. Aditi has submitted, and we're waiting for her results. Anil will be submitting shortly, and we'll also look at that. So maybe another 15 minutes I'll take. Then I'll give the last half an hour to Dr. Mr. Krishan Pal Singh, who is also about to complete in few months. But we are submitting two papers. It's under review. But yeah, we would just show the demo. We may not be able to share the papers. Maybe once the papers are published, you can look at that. But we are happy to share the work, no problem, because it will take a long time to understand dark web, capture the data and analyze the data. It's not so easy. And we have also not yet fully got into or got a live data. We have also tried to do a kind of mix and match, and let's see how it goes. So here is what I'm presenting in this RPL data. Here we are looking at two data sets, and we look at this RPL mechanisms, and RPL data sets are there. So we look at here is what I am trying to look at: the federated learning based anomaly detection for mitigating intrusions in RPL-based global IoT networks. This is the main work. Here I'm trying to talk about the privacy-preserving mechanism, because here we use what is called federated learning. Also, maybe the second one also may be of interest, because we used a hyperparameter-based deep learning approach for intrusion detection. So why am I trying to bring in these here is because it will actually help you to understand that, yes, something on network security can be done. And definitely, I am still doing a AI related and machine learning related work. Any of the network security work. In fact, any domain that you pick up, any broad area of research that you pick up. So many times these days, what is happening for PhD students, they are trying to look at the words AI, ML, DL, like that, and they are stuck there, right? Please move out of that shell. Maybe I'm just trying to say that, because it's a big world, and there's a lot of things to be researched, and you get into the research and then apply the same things that you like: AI, data mining, soft computing, machine learning, deep learning. Any of these things are the same. So maybe this time when I advertised for my PhD positions, I advertised quantum machine learning, and I got a student. Otherwise, nobody was taking quantum, nobody was taking dark web, nobody was interested in intrusion detection system or IoT security, or edge computing security and all. So obviously, we are using machine learning, but it's still not appreciated. So let me look at these two things of hyperparameter based deep learning approach and also the federated learning based approach. Let me take you there. Let us see if I can go there directly. Yeah. So this is the hyperparameter based optimization for this thing. So we are using a hyperparameter based deep learning mechanism for classification in RPL attacks. RPL stands for routing protocol for low power and lossy networks. You can look up Google, or you can read a little bit on what you call ChatGPT will give you a lot of information on RPL. RPL has an RFC. RFC is a request for comments, which is there on the IETF website. So you can go and look at what is RPL. And of course, our survey paper is there if you want to look at what the attacks on RPL attacks in IoT networks using RPL protocol or compromising RPL protocol. What are the attacks? You can read a little bit about that. I'll show you the survey paper shortly. Just before Krishan Pal starts explaining. Right, here is a solution which is analyzed on routing attack dataset, employing a scenario of dataset which are imbalanced and balanced using undersampling. It published in 10con, and you can also look at that. So this was a different solution, right? So hyperparameter based optimization, which tunes the deep learning model, is what was used. A tuner search will give the optimal hyperparameter for deep learning model, and the model is rebuilt with these parameters, right? So it will improve the overall classification accuracy. And the various hyperparameters are basic learning rate, number of neurons per layer, activation functions, optimization algorithm. That's so a combination of these things are varied, and you could get an optimization problem, and then you could do that, right? So there were many approaches which were used, and we could reach that. So basically, the hyperparameter optimization was the main contribution of this work, and then obviously the deep learning model was built and classification was achieved. So this is the basic idea that you look at. So there is a data set here, then you are doing some feature engineering, testing it, and then you have the optimization which is being done on the hyperparameters. Then this model which was built is rebuilt again here, and then a fresh classification comes in which gives you more better results. So hyperparameter tuning and model for binary classification was done, and it was simple normal systems we executed with more RAM, and we could use some model types. DNN, deep neural network, was used, and we had got various results from that. And moving from that, we worked on two data sets. One was called the Root 4 2023. It was a recent data set. So with hyperparameter optimization, how the result has improved is what is shown here. And then we moved on to another data set also. We try to look at that, right? The second one is a federated learning based anomaly detection for RPM. It's called the Flamingo. So we have a two-phase pipeline, which is called, basically you do the global aggregation model and the client model, right? So two models that you look at, and you can understand from this diagram where you have the local model and the global model, which is there, which helps us in privacy preserving. So privacy preserving machine learning, if you remember, PPML is achieved using federated learning. So this is another model which is there, and again internally local models and global models are there, as you can look at, right? And then we can see, so if this first one is MCDP, is the first process where you do the feature engineering and do the mechanism where you do the analysis and partition the data and all that. So you do the MCDP, and then you come to the global aggregation model where you use the local models and global models, where you can look at, and you have the global aggregation model, and you aggregate all of them using the federated learning model called the M global, and you get the results from that. This the total the global model is created, right? And then you run it using the TensorFlow libraries on Keras libraries on scikit-learn, and then you can get that. So this is various attacks which are there on two data sets which are used, Route 4 2023, which used in the previous contribution also, and then new data set called IRAD. Both the data sets are used, and then you know what is the data set and the distribution of the four attacks that are there, or the five attacks that are there, right? And then 6, 7, 8, 8 attacks are there, and you try to look at various multi-client distributions, C1, C2, C3, C4, C5, and then you test it, and then The binary classification and multi-class classification is there before you using various epochs starting from 10 to 100. And then again, you see the various deep learning models that are there, CNN, LSTM, RNN, and a combination of CNN, RNN, and CNN, LSTM, and how the results have varied, right? So this is what is being communicated now, and this is the results on IRAD dataset. So a lot of data sets are readily available, and you can and these are the comparison with these, and of course the data sets are same, and sometimes they are self-generated data sets, and how the performance has improved. Flamingo, how it has improved in a minor class and multi-class based on this data, and based on this data set, how it has improved in the multi-class and binary class, and what is the best results that have obtained. So these are how the things have improved, and we are submitting that for this work. So this is the kind of thoughts that the three students' work I have stated. And of course, we have another 25 minutes. After that, we'll take some questions. Meanwhile, if I'm able to look at that paper, yeah, if there are any questions, you can ask. Before Christian Paul is ready, he will share the screen, and he will share the two methods that we are using on dark web. A little bit of information on dark web I will share. Meanwhile, we'll do that one thread. Let me share what is dark web at least, so that you will understand how it goes, and then you can look at that. So this part I will minimize. Okay. So this is basically application of deep learning in IoT network. Full screen. Yeah. So if you look at what is a Tor or what is dark web, Tor is a protocol. It's called the onion routing protocol. This is the latest work that's going on in MNIT, what we're doing now. And basically, it's on an anonymization network. Now, there are a lot of data which is being generated, though it is an anonymization network. We're collecting the data and trying to analyze the data and give you a solution for that. So Tor network basically is an anonymization communication network. So anonymization, most of you may be understanding anonymization is where no information about the source is known. It's totally anonymized. We don't know where the data is coming from, who is sending the data. A good example is a blockchain where all the transactions are public, but we don't know who made the transaction, right? It's something similar. So, and then in this case, the data cannot be recovered also because it is encrypted, right? So it is moving through various nodes in an encrypted form and reaching the destination in an unencrypted form. So these are the onion services, and then these are the regular services. You can access the user here using Tor can access normal services and onion services. Onion services have websites which have .onion as an extension, and they cannot be accessed on normal browser. They have to use what is called a Tor browser, and Tor browser is nothing much different than a Mozilla browser. It is slightly modified, but then what it does is it anonymizes, and .onion sites can only be opened using a Tor browser. So first you connect to the Tor browser. The Tor browser connects to the Tor network. The Tor network gives you access to various .onion sites. These onion sites cannot be accessible otherwise. So there are multiple nodes in between called Tor relays. There is an exit node, there is an entry node. So there are a lot of entry nodes, a lot of exit nodes, and a lot of relay nodes in between, and they're all volunteers to participate in a Tor network. So if you create a Tor account, you become part of the Tor network, and you allow Tor traffic to pass through your network, right? Or through your system. You give your internet bandwidth usage for that, right? So that is how it is done. And so there is one system through which it goes in. It's called the Tor exit, Tor entry node. Once it goes into the Tor entry node, we cannot know what happened to the data, where it is going. And then it reaches the exit node. From the receiver, you can maybe reach to the exit node, who is the exit node and what is he doing. And beyond the exit node, and before the exit node and after the entry node, nothing is easy to identify. Of course, there are different mechanisms which you're exploring. So this is how the data goes. So the onion is created one layer at one step, one layer is added. So it becomes a full onion as you proceed. right? So the onion something looks something like this. The user first talks to what is called a rendezvous point. Okay, a rendezvous point takes you to the entry node. So the actual layer goes in, and after that, the pink layer you see, it is removed at the entry node. Then it goes to multiple relay nodes, and finally reaches what is called the exit node. By that time, some more onion layers are removed. So you see that there's only one layer removed at the exit node, and from the exit node, when it reaches the normal website or a Tor website, this last layer is also removed. Only the user request is sent finally, and it reaches the destination or onion website that you want. So this is the combination that you can have. So these are the variety nodes that I've already discussed: entry node, exit node, middle relay nodes, bridge nodes, directory authorities, which have it's kind of a DNS for the Tor network. Then hidden service directory nodes, which list all the websites, and then the introduction and no points, which help to give connection. They don't want to directly give you connection to the onion site, so they give you connection only to the introduction and the points. They tell us and connect you to the location. So that's how this whole network works, right? So anonymity is not security. So Tor can hide the identities, but then it doesn't give you safety. Tor was actually created to be an anonymous network for government and journalists to share information, but now it is a heaven for a lot of malicious activities. If you look at it, child sex abuse material, child pornography, most of the sites are based on dark web. Plagiarism software, plagiarism books, that's okay. Still, you use it for academic and education purpose. Drugs, uh, uh, ammunition like AK-47 and other things, cannabis, and marijuana and ganjai, common term. All these can be ordered on dark web. Passports can be ordered on dark web. Guns can be ordered. They will be delivered to your home. You pay using blockchain or bitcoins or something, and then you get them delivered at your home. I'm amazed at some of the things that are happening on dark web, right? But then who will monitor? Who will? What can be done? Who has designed it, and who is going to benefit from it? Is a big issue that we can do. So that's what we did, and we try to look at trying to analyze some of the things, because the traditional analysis is limited. A lot of handcrafted features are there, so very difficult to battle against evasive techniques. Tor's traffic is also complex. Access onion sites access is not available. Basically, some encrypted traffic patterns are available which you can analyze. So, but deep learning has advantages. So it learns the hierarchical mechanisms and non-obvious patterns. It doesn't miss any non-obvious, and it also adapts to traffic morphing and obfuscation and noisy data. So we used DNN, CNNs, transformers, and other things for that, and you can do that. So basically, classical machine learning requires experts to design the features. So basically, you have to understand how the mechanism is going on. Deep learning basically extracts useful features from the raw data, and it can find out these information like spatial patterns in packet bus, or sequential behavior in flows can easily be done. So there's very less bias, there is better generalization, superior adaptation to evolving traffic patterns. So these are the variety of things that are there. So some of the applications that are there that you can do. Website fingerprinting is one aspect that we'll discuss. Flow correlation of the network traffic flow is another aspect that we can look at. We'll look at both the things, and of course there are so many things that are there, but two of them is what we look at. So we'll discuss what is called hype prober. From here, I'll ask Krishan Pal to take over. Two papers we'll discuss. One is hype prober, and the other one is inspector mockingbird. So we'll try to look at that, and of course, on one of that we are writing a paper, so we may not be able to share that information. But mockingbird is already published, so we'll look at some of the codes that are there. So let us look at these aspects, and we'll conclude. So the paper. Can you give share access to the other? I will remove the share here. I'll show you the attacks on IoT towards the end after Kishan Pal takes over. Over to Kishan Pal. Can you
Can you
unmute the?
unmute the?
Yeah, it
Ah,
is.
yeah, it is.
Can you
Can you
unmute the other
unmute the
Emmanuel
other
Pilli?
Emmanuel Pilli?
Krishan Pal, you
Krishan
can
Pal,
check.
you can check.
Share karo.
Share करो.
Can you
Can you
unmute the
unmute the
other
other
Emmanuel Pilli?
Emmanuel?
Second one.
Second one.
Wait, both of them
Both of them
focused.
focused.
The permission is.
Permission is.
Am I audible? Good. Okay. So we should begin with hyperograph first. Share this screen. दिख रहा है थोड़ा zoom कर. So hyperograph is basically used for TOR networks relay capacity estimation. So we have seen how TOR network functions. So it begins from the entry node and goes towards the exit node. In between there are relay nodes, and we decide which relays to select on the basis of their bandwidths. And to manage this bandwidth, we do this relay capacity estimation, how much load a relay node can handle. So to do that, what we do, we divide the traffic into three classes. First is underloaded, second is normal, and the third one is overloaded. Okay. This complete experiment is conducted on a synthetic data. So we do not have to use the real traffic data, but the synthetic data is generated on the basis of real toll traffic data. So we know the basic what we require, what number of relay counts we require, what is the capacity, what is the threshold for high load, what is the threshold for underloaded traffic. So to know what is the true capacity, we use a Poisson distribution to simulate how much load a relay node is gonna require to pass the traffic from its circuit. When TOR build a circuit, it decides the bandwidth that it's gonna require to pass a particular packet from its traffic. So the initial classification is based on Bayesian prior posterior, Euban regression, and weighted average. So the relay load is calculated on the basis of recent load, what is the variance the recent load is had, and historical data, the previous traffic that has passed from that particular relay node. So and by doing that, we calculate a weighted average that divide our traffic into three classes we mentioned earlier. One is underloaded, one is normal, and one is overloaded. So by underloaded, we mean that a node has supposedly 1000 kV capacity uh, capacity, and it is passing traffic of supposedly 800 or 900 kb data. So this is what we mean by underloaded. What we mean by overloaded is plus minus 50. So like if a relay is passing 950 or 1050 kbs of data from 1000 kb bandwidth, so this is what we mean by normal data. And overloaded is when the data is gone beyond plus 200 kb from the allotted bandwidth. Now, so first we do the GNN based refinement. In this, what we do first we mimic the message passing from the historical data. We conduct a similarity graph on how previous performance were of this particular node. So let me go down there. Okay. Now this is the mean and standard based on the divergence draws of 2000 relay nodes. What is the sampling speed? How much time has elapsed? What is the step size? What the grad evaluation has been conducted on that? Based on that, we calculate the mean and the standard deviation and how much load the historical data is at previously. So this is this is calculated for all 2000 relays for all 9 columns, that like essential tail, what is the uh, MESE standard deviation, what is the bulk size, what is HDI. Once we do that, we go to the what number of requests we have received from each relay node. So here you can see we have we have 2000 relay nodes, and we calculate that what number of requests we have. So here we can see that relay 740 has given us 124.44 requests. Similarly, relay 751 given us 2149 requests, and this goes on for all the 2000 relay nodes. After calculating that, we go for how much allocated request sample size we have given to all these relay nodes. So here you can see, like for an example, relay 1240. So here you can see that relay 1240 was assigned to 56536 requests, and it has used around it has used around 513 requests. So here you can see that it is usually underused the request allotted to that relay node. So we will categorize this into the underloaded relay capacity. Similarly, this is done for all the this is done for all 2000 relays. So we categorize them into three classes which we mentioned earlier. So this practice is done with all 2000 relays, and after doing that, we do this. We distribute the estimated relay capacities of all the 2000 relays and what is the requirement. So this is number of relays up to going up to 800, and this is the capacity, estimated mean capacity we have allotted them. Uh, this is the posterior uncertainty distribution. Here, mean capacity estimate is SDI width is divided, and you can see these dots are the mean of each and individual relays on basis of their mean of capacity. And this bar shows that how much top 25 critical relay capacity has they have had around 94% of SDI, and similarly, this is system capacity report, and we calculate all that all these for all 2000 relays. Now, how exit relay capacity has capacity tracking historical data is on the box. We calculated like 16,000 exit relays, and what their true capacity was, what is their MLE calculation, what is their Bayesian calculation, and similar practices done for all. Now, these are the three classes we have constantly mentioned. One is underloaded. So this is the true capacity distribution and the error improvement of underloaded data. Then we calculated the same for the normal data, and then we calculate the same for the overloaded data. So here you can see that the middle node is very much clustered in the overloaded data, and the exit type and the entry node is clustered in normal data. Relay node is very much balanced in between. And here you can see the relay node is very much occupied, but it's not using that much of capacity, which was allotted to it in the underloaded capacity. And the normal performance is shown by entry and the exit node. Now, this is the high proper. High proper is basically TOR's relay capacity estimation. How much bandwidth we have allotted, how much capacity it is using on the based of the historical data to give us a more accurate assumption of what size of bandwidth we should allot, and what is the bandwidth it should be allotted to be selected in the circuit selection algorithm. And after doing that, we can put in like a better circuit. We can make an efficient circuit so it uses a minimal amount of bandwidth and still perform better than what existing mechanism is performing, because since tor uses so many around 5 to 7 node in between the client and the web server, so it is very much slow than our regular web browser like Mozilla and Chrome. And it is not it does not provide us the like the speed we are usual to in the regular browser. So by doing this, by reducing the sampling speed, by allotting the efficient bandwidth, what we do is we reduce the time between the relay selection, and we reduce the total amount of request time between the HTTP get and the HTTP response. We reduce the total amount of time. Now, second one is website fingerprinting. It is an attack on Tor. What website fingerprinting is like? There is an now from this diagram you can understand what website fingerprinting is. Is this visible?
Yes, sir, it's visible.
So in this diagram, you can see that user request is layered in like a multiple layer of encryption. It is what we could call onion layers. You peel one layer at each step by step. You peel one layer of encryption, and then you get the HTTP request at the rendezvous point, which connect us to the onion service or the web service which we require to connect. This is our user, and this is the onion service or the website we need to access. So the request is gone from entry node where it is encrypted in 3 layers. Then it goes to relay layer, entry node peel of one layer of encryption. then it passes the request to the relay node. Relay node again peel one layer of request, and it goes on until we get the HTTP request to the onion service. So basically, the idea was to uh, anonymize the entire communication and hide who is accessing what website. So basically, who and what are the questions which we need to figure out in website fingerprinting. So in website fingerprinting, adversary is on the entry point. It captures the traffic going from the entry point, coming from the user and going from the entry node. But it do not have any information about where it is going or what it needs to access. So basically, what it do, it create an individual fingerprint of each packet passing, and then it when the response is coming back from the rendezvous point to the entry node, it capture against the response of each request and do the fingerprinting again, and then it uses the deep learning to similar to like do a similarity analysis of which fingerprinting is connected to which response. So basically, this is the website fingerprinting in Tor. So yeah, so this is the data set we have used, or the Mockingbird paper we have mentioned. It is published in Transaction of Information Security and Forensic. It has number of classes, instance per classes, total instances, and the burst input size. The burst input size is the input which we give, which the entry node passes through in one window size. So what this burst input size is, it is padded using the encryption, and if the traffic is less than 750 bus, then it adds some salt in it, or if it is bigger than 750, then it truncate it, it divides into two parts, and then do this 750 communication. So basically, to connect all the dots is very hard, because we do not know what how much noise is in there in the circuit, what truncation is used, how much padding is done. So we need to address all these problems. So uh, these are the like defenses, the existing defenses. Either they are using traffic morphing, they are using traffic shaping, or they are using padding to hide real traffic with dummy packets. They send a few dummy packets in between the real traffic packets. So to like address this, uh, we have another solution. It is named Mockingbird. What Mockingbird does is it provide adaptive adversarial packets in between, so that the real traffic gets clustered so much that it is very hard to divide what real traffic is and what dummy packets are. It is basically an improvement over the WTF pad, since WTF pad was producing the dummy packets, and those dummy packets were very easy to identify, very easy to target because of that traffic sequence number, the packet sequence number. And since these are the dummy packets, they does not have carry any content in it, whether it was encrypted or non-encrypted shape. But what Mockingbird resolve, it provides each and every adversarial packet with an dummy distorted information of previous historical communication. What it takes all the previous communication, it create a distortion out of those previous communications, and then provide the dummy packet with an encrypted, distorted uh, content. So like this dummy packet does not feel an empty or a vacant. It provide and it does a sequence number to it also, so that it is very hard to organize all those packets in a sequential order, and it adds so much noise in it. So here you can see it uses CNN, 1D CNN and 2D CNN to like do this adversarial manipulation in the data. Then it uses yeah, it is using the channel first categorical cross entropy to calculate the accuracy of what is the loss of each packet in between on the basis of two attacks. One is deep fingerprinting and one is variance-based CNN attack. Variance-based CNN attack is to uh, remove all those distortions and see what real traffic is. So to address these two attacks specifically, Mockingbird uses 2D CNN to add the distorted packets. Yeah, yeah. Here you can see that what different threat models were used. So these are the different threat models. One is undefended, which is the tall traffic in its original nature. Then there are different padding and the defense mechanism on different threat models. One is deep fingerprinting, one is cumulative fingerprinting, one is K fingerprinting, one is K neural network, and then one is variance-based CNN. Here you can all see the different threat models and the different defense mechanisms which we have in like existing literature. One is WTF pad, it's a padding, it's adaptive padding defense mechanism. Then there is a walkie-talkie, it is again a padding defense mechanism. Then there is a proposed model is our own model which we have used to improve on Mockingbird. So this method is an adversarial padding method also. It is named Adapter. It's under review right now. And the last one is Mockingbird, which is in like a state of the art of existing literature. So here you can see that Mockingbird performs like way better on all different defense mechanism, but its performance on KNN is so much distorted. So we had to do something on that. So like how much defense mechanism is affecting the attack. So to improve upon that, we have to like give upon our own model, and we were able to reduce the efficiency of all the attacks in like from varying size of 33 to 19% on top two attacks which we mentioned of deep fingerprinting and like war CNN. Yeah, so these are the like different epochs we run to calculate the loss and the accuracy and all. Any questions on that?
Yeah. Thank you, Krishan Pal. And quickly, let me share. I think we have 4 more minutes, so let me just share. So we have looked at how machine learning is applied on various domains. We discussed, I think, 4 aspects. So one on cloud security, one on RPL attack detection, one disruptive event detection. The third one is also a security attack, but by and large, a natural language processing problem. Dark web, we have discussed the website fingerprinting and flow correlation. Kishan Pal Singh has presented. So if these papers are available, you can look at it. Of course, we'll share the slides, avoiding our this thing as much as we could show, that much we will share with you, and you can take it forward. Of course, when the papers come, Adapter and Hyprover, you can look at them in detail. Right? Of course, actually, most of the time we need to understand various domains. We don't know where which problem in which domain may be applied to our domain, because we are looking at a specific problem and the author may say we are addressing this problem and we use this technique and it's click for us, because we are also struggling with the same problem. Let's take that technique and apply it to ourselves. It works fine and you get the good results and the paper. So please keep looking at, because we are more focused on few domains only when we talk about deep learning, but there's a whole lot of things going on. I talked about core research on deep learning. So there are attacks on deep learning, security issues on deep learning. There are 14 generative adversarial network and generative adversarial attacks are what you can look at. So that's one solution, one problem. The second one is data and model poisoning. When you are creating models and when you are creating training, attacks can be done. And then obviously last as a solution also, we can look at federated learning as a how you can try to localize the data computation and a local model and the global model, so that the global model doesn't reveal anything. The local model does everything, only the results are passed on. So the actual working of the algorithm is not available anywhere. So that's something that you can look at. So these four aspects quickly, one slide on this, and I'll conclude. So basically, adversarial attacks are basically created to fool a trained model. Trained model, as I was mentioning, it's trained to detect dogs, but you show a cat and it says dog, or it shows a dog, you show a dog itself, you know it's a dog because you are able to visually identify it, but the model which is trained to identify dogs is saying it's not a dog. So, or it is something like there is a signs, you are looking at images, the sign says stop sign, and it says speed limit sign. So actually you should stop, you should not move forward, but it says you can go at 40 kilometers per hour. So that's a big mistake, right? Where you have to stop, you are actually, it is saying you can go. It bypasses facial recognition, malware detection, so many of these aspects. So the basic defense mechanism, some of them, as we look at, our adversarial training, input sanitization, and defensive distillation. You can look into any of the search models, and you can get various papers on this. You can look at the solution. So we have had run few models as MTech students have done this generative adversarial networks and generative adversarial attacks, actually adversarial learning or adversarial attacks, and then they have modified the few parameters in the data sets, or few values in the data set. So we look at the second aspect, which we call it the poisoning, data and model poisoning, where you can inject malicious data during training to influence model behavior. So poisoning attacks are very important. So you can look at poisoning attacks. So a poisoned participant in a federated learning introduced biased updates. So that's how, if you make one change, one local model is compromised, so the whole model fails. So targeted misclassification or model backdoor will be there. So defenses are robust aggregation, data validation, and Byzantine resilient federated learning. Of course, various solutions, various modifications have been done. The third aspect is basically the privacy attacks, which are basically membership inference. You could identify whether this class or this data was used in the training. So if you're able to determine those, then you can influence how the data will affect the training, and you can be able to guess how you can try to do that. Model inversion, reconstruct the training inputs. What were the training inputs that were given? So you do the reverse engineering kind of thing. You reconstruct the data. There's a gradient leakage where you recover data from model gradients. This is also possible. And of course, defense is basically you maintain differential privacy and secure aggregation. Some of these mechanisms can be explored. Lastly, of course, detail on membership inference. Attacker infers if a specific data point was used, as I was just mentioning. So maybe example is a testing if a patient's record was used in a medical model, and there's a dangerous implication if such things are leaked. So it's a privacy leakage from sensitive data sets like health records. So differential privacy, dropout, obfuscating confidence scores, all these things are different solutions, right? The intellectual aspects also here, attacks on intellectual data that are there, IP attacks you call it, or the intellectual property, which is very important. It's a personal information. If somebody steals, you lose the royalty rights and all. So basically, somebody may want to steal the model stealing. So copy the model behavior by using API. So you're testing something and somebody is actually observing what you're doing and he's trying to steal the information. Evasion attacks, so avoid detection at inference time. Surrogate models may be built from the API output. So the defense is query rate limiting, and output perturbations should be. So these are different solutions that you can look at. Federated learning, I give it as a solution. Collaborative machine learning where data remains on device. Only the model outputs are shared. So the entire data doesn't go out. So that's where it is. So for phones training voice models without uploading the actual audio. So only the audio pattern goes, the audio doesn't go, right? It enhances data privacy by design. So that's where federated learning is very much used. So please explore. It's slightly difficult, but then there are now a lot of content has come in and you can easily do it. Initial days was very difficult, as I talked about 2010, 12, things were very difficult. Now everything is possible. The BTech students spent about 3 months to generate a data set. Now generative AI model will generate in 1 week. So that's the time saving and that's the comfort that you're getting. So it's easy. Challenges that are there basically in federated learning are obviously susceptible to poisoning and leakage by gradients. These are all the terms that I've used are all research challenges. So you can pick up those and do that. So security aggregation, differential privacy, encryption, all are solutions. Attack where all it can be taken, data can be done where you are doing poison samples or label flipping can be done. Model which is exposed architecture and APIs, training pipeline and compromised nodes where you can update the injection and do that. And of course, you will also have inference interface, query-based exploits. You can do that. So the common defense, adversarial training for robust inference, differential privacy to protect training data, secure aggregation, federated learning, input sanitization to detect backdoor triggers, and access controls to limit exposure via APIs. So these are some broad solutions that I've given. Of course, this I should have dealt some in detail, but yeah, because of so many things, I wanted to show you hands-on and give you some uh, case studies so that will give you an idea that how deep learning can be used in security. And I think I did my job. If there are any questions, I'll be happy to answer. I'll be sharing the slides and I'll cut out some of those published work is there, papers you can refer. I'll put those papers, the references of those papers that you can refer for various machine learning in security aspects. I'll put you some of those slides I can share definitely because already it's published work.
Sir, would be very helpful if you are telling about case studies and all. So if you can share with our participants.
Yeah, that's exactly the 4 PhD presentations that are there. I will cut out those slides and we will create a separate PDF and the published papers I'll share so that you can share with the participants. Papers are anyway, you can also look up. It's very easy to find those papers. If you want,
Yes,
I'll share.
yeah. Okay, sir. We thank you so much. Your talk has really like deepened my understanding. I think all the other participants' understanding also about cybersecurity and deep learning aspects of security applications. So, I truly appreciate your time, wisdom, and contribution, sir. And we look forward to engage with you further, sir, and host you again in the future.
Sure. Thank you so much, and happy to be part of the first
Summer
summer
school.
school on deep learning. So I was very happy. Now my interest is on dark web and quantum. So maybe we'll intersect with quantum deep learning or quantum machine learning. Shortly, one of the student has joined on quantum machine learning now. So we'll try to hopefully, yes, you will hear more from me. Thank you so much.
Sure, sir. Thank you so much, sir. Thank you.